Okay, big moment. This is the video where we are going to cover the last technique for solving first order differential equations that you will be responsible for. It is another kind of substitution, and this kind of substitution is what's called a Bernoulli equation. So you look at this, and a lot of people are like, oh my, I know Bernoulli from my fluids class or whatever. Well, it turns out that, as a matter of fact, the Bernoulli that came up with this kind of equation and solution technique and so on, not the same Bernoulli as the fluid mechanics Bernoulli. In fact, the Bernoullis, let me tell you, back in I think the 1700s, were one hell of a smart family. Like, we're talking the family of geniuses that spanned a couple of generations. I wrote some of the names down on the board there. There's like a Nicholas Bernoulli that did like differential equations and probability. There's a Jacob Bernoulli, which did like who was a mathematician that did some calculus stuff. There were Johann 1, 2, and 3, and there were various mathematics people and physicists and all this kind of stuff. The fluid mechanics one, that's Daniel. Absolutely ridiculous. Imagine that, like, that's just what your whole family did, and they were just really, really prominent mathematicians. The running gag that I kind of like to say is that there must have been some like Billy Bob Bernoulli that worked at the corner store that nobody likes to talk about and so on. But like, to be honest, I have the greatest respect for those kind of people and those kinds of jobs as well. So I won't make too much fun. But there is a really remarkable family here that came up with a lot of cool stuff. So we're going to talk about the Bernoulli equation, and I don't even know which of the Bernoullis this was. So just take for granted it is one of them. So these are differential equations that I like to say that they look almost linear, but not quite. So let's read this equation really slowly and together and see what it says. You see a y prime and you're like, okay, that looks like a first order equation. And you see plus p of ty and you're like, oh wow, this really does look like a first order linear equation. No problem. And then you get to the right hand side, you see a q of t, that looks fine, but it's hit by y to the n. It's hit by this thing, which makes it nonlinear, and which means that you can't use those first order linear techniques to solve. That being said, this kind of differential equation can always be solved by a particular substitution. And what I want you to know is how to use this substitution. This is gonna be one of those substitutions that I expect you to be able to recognize when you see an equation of this form. So what you're gonna do is make a substitution of a brand new variable, v, and it's gonna be y to the power of 1 minus n. Y is the old dependent variable, so we have a new dependent variable that's a different power of y. And it turns out that this always reduces things down to a linear differential equation. Okay, we're going to go through one example to kind of demonstrate this. So this is going to be a pretty short video, but the first step for any of these sorts of things is to divide the equation by y to the n as a first step. When you do that, it's going to make kind of what to do, where to go next, kind of jump out at you when you go to do that substitution. Oh, and look at that. I actually did put the name of the person down here. It was Jacob Bernoulli who came up with these, and he's also the guy that discovered the constant E. Weird that constant E was actually named after Euler, but I mean, E sounds so much better than B. Imagine if we had a constant B equals 2.718. No one would like it. We wouldn't imagine B to the X. I don't know. Anyway. So there are lots and lots of other Bernoullis. That's what this is right here. But let's move on to this example. We just have this one example to get through here. So we have a differential equation, and it doesn't look like it's quite in the form that we would typically like. Well, I mean, I guess, so the difference here is that I have a t squared in front of that y prime term. You could put it into standard form first, and you would equivalently get to the right spot. The important thing, though, to see this is a Bernoulli equation is the fact that you have a y prime term right here, you have a y of t right there, and this here, this y cubed, is what makes this into a Bernoulli equation with n equals 3. So this equation, this dE is Bernoulli with n equals 3. That's not a double factorial, that's me being excited. So it's a Bernoulli equation with n equals 3, and so therefore we know immediately to substitute the following. V equals y to the 1 minus n. In other words, for this example, we're going to substitute v equals y to the 1 minus 3, or v equals y to the minus 2. Okay, seems like an interesting thing. How is that going to help? Well, let's check it out. In order to make that substitution, I don't even see a y to the minus 2 anywhere, but remember my advice from that last page. Take your first step and divide the whole equation. Divide the dE by y cubed to start. And if you do, it becomes this. Oops, let's just not do that. It becomes, and we would get, okay, I'm going to leave this t squared here. Again, you could have divided this off to start, but we're going to see by the end it won't matter, I think. But I get 1 over y cubed, y prime of t, all right, plus, okay, I've divided by y cubed, so I'm going to get 2t, and then I have a y divided by y cubed, that's 1 over y squared. Yeah, that's all I get, right? And then on the right, I'm going to get equals 1. So I have this as a result. You know what, I guess I don't really like the of t there, because the y is, this is the derivative of y. So remember that y is the dependent variable, and just write y prime here, just to be consistent. So we have t squared 1 over y cubed y prime, plus 2t 1 over y squared, equals 1. Okay, so there are a couple things here. First of all, doing that division, immediately we can see that this appears right there. So this quantity is really just v. There's one better thing, and this will always happen. Watch what happens when I go to take the derivative. I need an expression for y prime after all, so I need to take the t derivative of both sides of this expression right here. So v prime dv dt, remember that's what that is, I'm going to get here, oh, I guess I'm taking the derivative of this right there. I'm going to get minus 2 y to the minus 3 times the derivative of the y with respect to t, y prime, right? If you need the dt to see this, right, remember that y prime is dy dt. Remember that the v prime is dv dt. If you need to write that down to make sure that you see that you need chain rule there, to make sure that you get this right, do so, okay? That prime notation can get in the way if you're not super comfortable with the background. Anyway, let's take this. Actually, let's not quite take this. Let's almost take this. This is going to be the same thing as saying, watch, I have a y to the minus 3 here. I have a y to the minus 3 right there. I have a y prime right here. I have a y prime over in the equation. I'm going to divide by the minus 2 before I do anything. I'm going to go minus a half. V prime is equal to, well, y to the minus 3 is 1 over y cubed, so I'm just rewriting that, y prime right there. And you see what the beauty is. Not only did that expression here make up a good v in that second term, but this expression here lets me convert that first one so that this quantity here can be represented completely in terms of v. And it would be just minus 1/2 v prime. So I can take this equation and boil it down into something where it only involves v. And that's what we're going to do. The dE becomes the following. So the t squared that's here is just kind of sitting back and watching as we go crazy here. But I'm going to get minus, looks like minus 1/2 t squared v prime plus 2tv equals 1. So I've taken those three terms, the 1 is just the 1, but I've replaced the 1 over y squared with a v. I've replaced this collection of y stuff with minus a half v prime. And you see what I have now? That's a first order linear equation. It's a first order linear DE. And you see, if I had divided by the t squared first, I just would have had a different sort of thing. I'm at a point where I'm going to have to put it in standard form anyway to figure it out, because that's how we deal with linear differential equations. So I just didn't want to do that step twice. All right, so let's do it. Standard form first. This should be pretty okay at this point. If you've been practicing at all, especially for the first test and so on, this should be pretty comfortable. I'm going to get v prime. I'm multiplying everything by like a minus 2 and dividing by t squared. So I think we get minus 4 over t. Is that right? Let me just see. If I multiply by minus 2, I get minus 4. If I am dividing by a t squared, I get a t on the bottom. Yep, I like this. V. On the right, I'm going to get a minus 2. And I'm going to have over t squared. All right, that's standard form, and it's a linear equation. I have to go and find an integrating factor and do all of the things that I normally would for a linear DE, but they should be things that you're comfortable with by now. So, integrating factor, that's going to be e to the integral of minus 4 over t dt, which we should be able to solve at this point, e to the minus 4 ln of t plus c. And if you do all of those steps and so on, this is going to be e to the, let's see here, ln of, 1 over t to the 4, right? Because of the minus 4 coming up in the exponent using that log rule, c can come down. I cancel these out, choose the c, and we end up with an integrating factor that's just 1 over t to the 4. So that's my integrating factor. I'll just box this up in another cloud, or cloud it up, I don't know. And we are going to multiply through by that integrating factor. So multiply through. If we do, we get 1 over t to the 4 v prime minus 4 over t to the 5, if I am doing that multiplication right, v equals minus 2 over t to the 6. If you've been practicing, you know that we're looking for product rule backwards to happen on the left. And if you see the 1 over t to the 4 there, well, we know that t to the minus 4 has a derivative of minus 4t to the minus 5. So you can see pretty easily that the function right here has a derivative that's right there. And we're able to have some confidence that what we're doing is correct. So we're going to keep going. Product rule backwards. Product rule backwards brings us to 1 over t to the 4 v all prime, this should be a t, equals the right-hand side, minus 2 over t to the 6. We integrate, and if we integrate, as usual, the prime comes off the left. I integrate the right, it looks like it's just a power rule. Make sure you get this right, you know. It's going to be minus 2, we go up a power to minus 5 over the minus 5. So I think we should get a 2 over 5 with a t to the 5 on the bottom. Let me just make sure that that's true. I think that's good. And don't forget your plus c. That means that v, if we isolate for this last step, we end up with v equals, and then multiplying by t to the 4, 2 over 5t plus ct to the 4. Like that. Oh, but there's one last step. Don't forget it. Usually isolating is our last step, but of course v wasn't our original variable. What was our original variable was y. And y, we had v equals y to the minus 1/2. So we have to convert back. So we have a y to the, did I say 1/2? I meant 2. Y to the minus 2. Y to the minus 2, whoops, just lost my, there we go. Y to the minus 2 is equal to that 2 over 5t plus ct to the 4. And if I think about what this means 1 over y squared. So if I take the reciprocal and then take plus or minus the square root, we should be good. So I'm going to get y equals, okay, ready? It's plus or minus the square root of 1 over this stuff. A couple things here. It's really easy to just want to take the reciprocal of each. That's not an option. That's not true. It's 1 over the whole thing. And yeah, that's about how nice it is. You could take that square root and apply it just to the bottom, because we know that the square root of 1 is 1 on the top. So there are a few different ways to write it, but I'll leave it here. So that is going to be our last example of solving first order equations. And hopefully you were able to follow all of these. I totally guarantee there's some that are more straightforward, there are others that are harder, but all of these are things that you can get with practice. So practice, practice, practice. Contact me if you need help. And finally, I apologize because over the last minute I've gotten 2 emails, and you're hearing the notifications for them because my phone's volume is up. And so what do? We've had people complain about that sort of thing because it's, you know, they think that they got messages and stuff like that, but you know, I'm a human being trying to do my best with what we've got. We're through the first part of the course now, and you know, I've been thrilled to see so many of you working with me. So keep up the good work. Thanks for your patience, even through like ghost notifications and difficult, almost exact differential equations and all of this kind of stuff. Keep practicing. I hope to see you in office hours or send me an email. And for now, take care of yourselves.